This is lecture video 37, and in this lecture we will cover how we apply substitutions for definite integrals, and then we talk about how to find areas between curves. And here the following formula shows how the limits of integration change when the variable of the integration is changed by substitution. You see, we are applying a substitution here from the variable x. We move to the variable u, and as you can see, the boundaries of the integration are not from a to b anymore. These are the new boundaries in terms of your new boundaries u. Okay, so what is happening here? Let me explain. We are choosing a substitution here. Okay, our substitution is u equals g of x. So we choose this part as u, and this part is exactly du, right? If you take the derivative of both sides with respect to x, you obtain this. So it is easy to rewrite the insider part of integral in terms of u. It is f of u du. But what about the boundaries? You cannot write from a to b here because these are the boundaries for your here, a and b are the boundaries for the variable x, obviously, because here the integration is with respect to x. So these are the boundaries for x. Now, on the right-hand side, you are integrating with respect to du, so that you need to find new boundaries of your new variable u, okay? So here, these two are boundaries for the new variable u, not x, but u. Okay, changing the variable by substitution from x to u is a method to rewrite the integral and evaluate it easily. And by doing this substitution, you also need to change your boundaries from boundaries of x to the boundaries of u. So let's try to understand all those details through this example. We want to evaluate this definite integral by using a substitution. Okay, which substitution we should choose? Let's try this part as our u. Then du is derivative of ln is 1 over x, so dx over x, right? You see, this part is exactly du if we choose this part as u. So rewriting the integral in terms of our new variable, 1 over 2 can go out, dx over x is du, and at the denominator we have square root of u. What about the boundaries? You cannot put from 2 to 16 here. These are not the variables for u. Be careful. They are the variables for x. They are the boundaries for x. So here, instead of automatically putting 2 and 16, which is wrong, you need to find the new boundaries for your new variable u. And from this line, you can find your new boundaries, because if x is 2, what is u? U is ln 2. If x is 16, then u becomes ln 16. So you see, these are now the new boundaries of your new definite integral. That's why here I need to put from ln 2 to ln 16. These are the new boundaries for your new variable u. Okay, now it's perfect and we are ready to evaluate this definite integral. It is the integral from ln 2 to ln 16. What do you have here? You have u to the power 1 over 2 du. This is a power function. You can integrate it easily by using the power rule. You add 1 to the power, you divide by the same power. You are not putting an arbitrary constant anymore, because this is a definite integral. Instead of writing plus c, you need to insert upper-lower boundaries here, from here to here, okay? So the result is 1 over 2. In fact, these 1 over 2s are gone, right? They are simplified like this. So the result is, insert the upper boundary, ln 16 over 1 over 2 minus ln 2 over 1 over 2, or you can write it in the square root form, like this one. ln 6 square root of ln 16 minus square root of ln 2. This is your result, okay? So let's move on. Now we will talk about how to find definite integrals of symmetric functions by using some shortcuts. Okay, let's say our function is an even function. Okay, I will try to explain these two statements to you. Okay, first of all, we assume that f is even. Even function is defined as this. If the images of x and minus x points are the same, then you call your function as the even function. For example, the simplest example of an even function is what? Y equals x squared, of course. Okay, let's use this simplest example. Y equals x squared is an even function because at x and minus x, they have the same image, and we want to integrate from minus a to a now of this function. We want to find the definite integral of it from minus a to a. F of x dx, and this definite integral corresponds to the area on these shaded areas, right? And since an even function is symmetric with respect to y-axis, okay, as you can see, this graph is symmetric with respect to y-axis. Even functions are symmetric with respect to y-axis. That's why if this area is A, this area will be also A. So from minus A to A, integral of f of x dx will be the same as from 0 to a f of x dx times 2. So it is, in fact, 2a. Okay, now let's talk about odd functions. If your function is odd, then it will satisfy this equation, and the simplest example of an odd function would be y equals x cubed also, of course. So this is the graph of x cubed, and x-axis, y-axis, this is y equals x cubed curve, and you still want to integrate from minus a to a of this odd function. And this is an odd function, and it is symmetric with respect to origin, as you can see. Symmetric with respect to origin. That's why if you integrate it from minus a to a again, and if you consider this part and this part, the shaded areas, what you have. So it is from minus a to 0 f of x dx plus 0 to a f of x dx. I just can divide the integral into two parts like this. And from minus a to 0 f of x dx, can it be expressed in terms of these shaded areas? So from minus a to 0, since your graph, the curve is negative, the result of the integral will be negative. So the integral is a negative quantity. That's why it is still related to area, but minus of that area. And from 0 to a, no problem, your curve is positive. The result of the definite integral will be the same as the area. So the result is what? Is 0. Okay. That's why if you have an even function from minus a to a, the integral of it is 2 times from 0 to a. If you have an odd function from minus a to a, this definite integral, the result will be 0. And here are more general even and odd function examples. I gave you here the most simpler ones like x squared and x cubed, but look at this one. In the first graph, you can see that it is symmetric with respect to y-axis, so this function is an even function, and here you can see that it is symmetric with respect to origin. So this is an odd function. And here, if you try to integrate it from minus a to a, f of x dx, what you will find, as you can see, these shaded areas on the right and left are the same area, so you can just multiply by 2 the integral from 0 to a. And here, let's name the areas. If this is A1, this will be also A1. If this is A2, this will be also A2 because this graph is symmetric with respect to origin. And if you integrate it from minus A to A, what happens? So A1, it is A1, A2 contributes negatively because your curve is negative there, and plus A2 again, and here over this part, A1 will contribute negatively because you have a negative curve there. So you see everything is simplified so that you obtain your result as 0. Okay, let's move on. Now we will talk about areas between curves. So look at this graph. You have an upper curve here, y equals f of x, and you have a lower curve, which is the yellow one. The equation is y equals g of x. Okay, and what we want to do is to find the area between them. So can we compute the area between these two graphs? It is possible by using the definite integral. Area between curves. Okay, so how can we use definite integral to compute this area between these two curves? It is kind of integrating all those sticks, lengths of all those sticks, right? So integral of the length of all those sticks will give you the shaded area because integration is somehow a continuous summation. So what is the length of this green stick here? You will subtract the lower curve from the upper curve like this. If you take the difference, it will give you the length of this stick. So if you integrate this length of that line from where to where over this interval, of course, from A to B, so the integral is with respect to the x because you are summing up all those lines over x-axis. So if you do this integration with respect to x, the result of this definite integral will give you the area between curves, okay? So that's simple. You will just take the difference of the curves. You will subtract smaller curve from the bigger curve or the lower curve from the upper curve. You integrate over your interval, and the result of this definite integral will give you the area between curves, okay? So first example. Okay, we want to compute the area of the shaded area here. So we need to divide it into two parts, like from 0 to 1, the upper curve is x squared, and the lower curve here is, in fact, y equals 0 line. Okay, dx plus from 1 to 2, what happens? The upper curve, the equation of the upper curve is 2 minus x minus, again, the lower curve is y equals 0. So like this, dx. If you compute these two integrals and sum them up, it will give you this shaded area. Okay, let's look at this example. This time, okay, we have a pink curve here whose graph is given by this equation. We have a blue curve whose graph is given by this expression. And what we want to do, we want to compute the area between curves. Okay. As I explained here, we will take the difference of the upper curve and the lower curve. And as you can see, over the interval from -2 to origin, the upper curve is the pink one, the lower curve is the blue one, okay? And over the next interval from 0 to 2, the upper curve is now blue one, the lower curve is the pink one. So upper and lower curves are switching after origin. That's why we need to divide the integral into two parts again. So it will go like from -2 to origin. What is the bigger curve? Over this interval, this one is the upper curve, the pink one. This one is the smaller one, lower curve. That's why I will take the difference of these two, like I will subtract smaller one from the bigger one. Bigger one is given by this expression minus the smaller one. Smaller one is given by this expression, right? Okay, so you see I take the difference of them and my integral is with respect to dx. Plus, now on the right side, what happens? Now from 0 to this point, which is 2, this time the blue curve is the bigger one, so bigger minus the smaller I will write. Upper curve minus the lower curve. Pink one is the lower one on the right side. Like this, integral is with respect to the x. You see, we always take the difference of the bigger curve and smaller curve, upper and lower. Okay, instead of writing bigger and smaller, I think better to write upper and lower. This is the upper curve, this is the lower curve, and then they switch after the origin. They switch the places, that's why upper curve is this one now, lower curve is this one. So this integral is a1, where a1 is here, and this integral gives you a2, where a2 is the right part. Okay, areas between curves can be computed by definite integrals like this. You should only be careful about which one is the upper curve, which one is the lower curve. And areas between curves can also be computed with respect to y, meaning that a definite integral in terms of dy. This time, instead of considering vertical lines, we will consider horizontal lines. Okay, so you see x equals f of y curve is this yellow one, x equals g of y curve is this blue one. Now, you will consider exactly the symmetric of what we did above, and we will be integrating all these horizontal sticks, lengths of all these horizontal sticks through y-axis. So what is the length of this stick then? Again, the idea is the same. You will take the bigger curve, okay? Bigger curve is f of y minus the smaller curve, which is g of y. So this difference gives you the length of this stick. That's why now I can express the area between these two curves as a definite integral. This time we are summing up all those lines of this sticks through y-axis, so the integral will be with respect to y. And here I will write the difference of the functions as it gives me the length of this line. So upper curve minus the lower curve horizontally. Horizontally, f of y is bigger than the g of y, so bigger curve minus the smaller curve, okay? And here you will write the boundaries on y-axis from C to D, from C to D. Everything is with respect to dy, and on the boundaries of your definite integral, you put boundaries on y-axis. Okay, let's apply this in the next example. We want to find the area between these two curves, pink one, blue one, and as you can see, you need to work with these horizontal lines. What is the length of this horizontal line? It is the upper curve, the bigger curve, okay? This is the bigger curve horizontally, and this is the smaller curve now horizontally. So 12y squared, 12y cubed, this is the bigger one minus the smaller one. 2y squared minus 2y dy. You should take the integral because you are working horizontally with respect to dy now, and I will write the boundaries of y. The integral should be over this interval on y-axis, which is from 0 to 1, okay? These are the boundaries of y, and the integration is with respect to y here. You always subtract the smaller curve from the bigger curve. That's what we have done here. This was the bigger one horizontally, and this was the smaller one. Okay, so our final example for this lecture is this one. We will try to find the shaded area. Okay, for this example, it is possible to work with both with respect to x or with respect to y. One of them is shorter, but I will show you both of them. So first way is to compute this shaded area with respect to x. Okay, so if you want to do with respect to x, you need to use these vertical lines, and you need to subtract lower curve from the upper curve. But be careful, up to this point, the upper curve is the blue one and the lower curve is the pink one. But after this intersection point, the upper curve is changing to this black one. That's why you need to find the total area with respect to x. You need to divide the integral into two parts, okay? Where you will be computing a1 plus a2, okay? So a1 plus a2, where a1 is from 0 to 1. What is the bigger curve? Bigger curve is this one, where the equation is given by y equals x. Lower curve, I mean this part, is given by this parabola. It is x squared over 4, so the integral is with respect to x plus. Now we concentrate on a2, okay? This part. So we are doing it into two parts, the green part and the blue part. Okay, so now from 1 to 2, because this point is 2, from 1 to 2, this time the bigger curve is y equals 1 line. So 1 minus, again, the lower curve is the same, given by this equation, like this. Okay, so this is bigger, this is smaller on over a2, and this is bigger, and this is the smaller curve over a1. So if you divide the integral into two parts like this, you can compute the total area by taking these definite integrals with respect to x, but you have to compute two definite integrals. Second way is to consider this shaded area, this total shaded area, with respect to y, not with respect to x, but with respect to y. So let me draw the same curves again, like this and this. So this time, okay, this is y equals x line. This time is, this curve is y equals x squared over 4, and this is y equals 1. And so this is y equals 1. This point is 1. All the details are given there. Okay, this time I will consider horizontally, okay? You see, if you consider horizontally, you don't need to divide the integral into two parts. So, because always the upper curve is this one, and always the lower curve is this one. They are not changing or switching to other curves. That's why you can handle the total area by constructing just one integral. Okay, this time total area goes like, you can express it in just one integral because upper level curves are always the same. Okay, and let's take the difference of the bigger curve and the smaller curve. And you should be careful that the integral will be with respect to dy this time. From where to where? Now you are interested in y-axis, not x-axis anymore, but the boundaries on y-axis. So the integral boundaries are from 0 to 1, which are these points on y-axis. And now the curves. The bigger curve horizontally is this one. And if you are doing the integral with respect to y, everything should be written in terms of y. So you cannot just put here x squared over 4. No, this is totally wrong because you should transform the equation of this curve with respect to y. So x equals some g of y. In this form, you have to write the equation of your curve. So what you have is x equals square root of 4y, right? So that's why this time bigger curve is x equals square root of y minus x equals y. So that's it. You see, writing the area between curves with respect to y is much more simpler than writing the area with respect to x, but both will give you the same result, okay? Okay, we can evaluate the integral and then stop there. What is the integral of this thing? You can use a substitution there. Okay, so you can put this one as u and then dy will be 1 over du. So the integral of that thing is 1 over 4 square root of this, right? 2 times square root of this minus y square over 2. And then from 0 to 1, you will insert these boundaries. Okay, so let me write like more details. Okay, how do you integrate this? I want to write the details here. If you choose this part as u, then what is du? Du is for dy. So dy is in fact du over 4. That's why you are in fact integrating square root of u 1 over 4 du. So what is the integral of this thing? Add 1 to the power, divide by the same power. 3 over 2, 3 over 2, 1 over 4 is already there. So, and then you will insert the boundaries. So it is back substitution for y over 3 over 2 over 3 over 2 times 4 like this, and 0 to 1. Integral of this expression is like this from 0 to 1. And then I'll stop here. Thank you for your attention.